We have discussed compatible and incompatible observables. Now let's discuss the uncertainty relation. For an observable A, we define an operator delta A is equal to A minus expectation value of A, or A minus average value of A, right? So this operator delta A gives us the deviation, of A from its mean value, all right, or average value. Okay. So here we see that this is an operator and this is a number. So you should understand that there's an identity operator there. Right. So the expectation value is taken for a certain physical state under consideration. Right. So whichever state you are considering, we take the expectation value of A in that state. All right. Now the expectation value of the square of this operator is known as the dispersion of A, or the uncertainty in A. Uncertainty in A. All right. So the expectation value, not the expectation value of delta A, but the expectation value of delta A square. All right. This is what we call the uncertainty in observable A. Okay. So this is called the mean square deviation. The mean square deviation or uncertainty. Mean square deviation or uncertainty. Okay. Now you might at first think, why don't we take just the expectation value of delta A, right? We have already defined this deviation, but if I take the expectation value of delta A, I see that this is 0, right? The average value of delta A is average value of A minus average value of A, which is 0, all right? So to characterize uncertainty, all right, or the deviation, to characterize how much it deviates from the average value, we take the mean square deviation, right? We take the expectation value of delta A square. And this is called the dispersion or uncertainty of observable A. We have got delta A is equal to A minus average value of A, or A minus expectation value of A. This is the deviation. All right. What's the squared deviation? It's delta A square. That's equal to A square plus square of the expectation value of A. All right. Square of the expectation value of A minus twice A multiplied by expectation value of A. All right. Now I can find, let me write here, right? I can find the expectation value of delta A square, right? That's the mean square deviation, right? So I just take the expectation value on both sides. Here, the first term is A square. So I've got the expectation value of A square. So first you square and then find the expectation value in the given state, all right? In whichever state that we are considering, right? Plus, this is square of the expectation value of A, all right? Square of the expectation value of A. All right, this is already averaged. This is already an average value. So if you average once more, it doesn't change. Right. So this is already an average. So average of an average is again the same thing. Right. So that's the reason why there's no change in this term. Right. Minus, here I have got twice A multiplied by average value of A. When I take the average, it becomes twice average value of A, average value of A. Right. This I can write as square of the average value of A. Right. So I see that these two terms, right, here I have square of the average value of A, and here also I have square of the average value of A, or the expectation value of A, square of the expectation value of A, and here also I have the square of the expectation value of A. All right, so this can be written as A square average minus average A square, right, square of the average value. Okay, so that's why we have written here the expectation value of delta A square can be written as average of the square minus square of the average, all right, or average expectation value of the square minus square of the expectation value, right? So this we can define the dispersion or mean square deviation like this: delta A square average is equal to, right? We could actually start with this, right? In a given state, we first find, if you want to find the uncertainty in an operator, for example, all right, this is how we'll calculate it, right? So we'll write like this. If we want to find the mean square deviation of an observable, this is how we'll calculate it. The average value of delta A square is equal to, okay, we can write it as, first you find square the observable and then find the expectation value, right? So expectation value of the square minus square of the expectation value, minus square of the expectation value. All right, so here we are squaring the observable first and then finding the expectation value. All right. Here we are finding the expectation value first and then squaring it. Right. So this you can take as a definition of dispersion. Right. You can take this as the definition of dispersion. Okay. Now sometimes the terms variance and mean square deviation are used for the same quantity. Right? This is also called variance or mean square deviation. Right? All these things, all these words are used to characterize the uncertainty or fuzziness, the spreading out, the dispersion, all right, in the observable. Right? So you can take this as the definition. You can take this as the definition for dispersion. Okay. So here is our dispersion. Average value of delta A square is equal to expectation value of the square of A minus square of the expectation value of A. All right. Now suppose the state that I am taking here. All right. Suppose the state that I am considering here is an eigenket of observable A. All right. Suppose state is an eigenket of observable A. All right. Then this can be written as, I can write this expectation value of delta A square is bra A prime delta A square. So this is the state, right? Delta A square ket A prime. This is the state. This is the state that we are considering. This is the state in which you need to find the dispersion of this operator. All right. So this is equal to, I have a bra A prime A square, or I can write as AA, ket A prime minus A prime bra A prime A ket A prime square. All right. So if I look at this, this is equal to, I can use the eigenvalue equations here. Right. Since this ket A prime are the eigenkets of A, as we said, we can use the eigenvalue equation. So we can use the eigenvalue equation twice actually. Once A acts on ket A prime and I get A prime multiplied by ket A prime, and here again A acts on ket A prime, I'll get A prime multiplied by ket A prime. All right. So this A prime square can be pulled out, and what I have is ket A prime, sorry, bra A prime ket A prime minus, okay, here again I can use the eigenvalue equation, right, and I can pull out the eigenvalue, and there's already a square here, so this is A prime square multiplied by ket A prime, sorry, bra A prime ket A prime, and what is this? This is equal to 0. All right. So if I take an eigenket, if the state is an eigenket, then there's no fuzziness in the observable A. But in that state, there's no fuzziness in the observable. There's no uncertainty. Right? We already have seen this. All right. If the state is an eigenket of A, and if I measure observable A on this state, I'm sure to get the eigenvalue A prime. Right? I'm sure to get the eigenvalue A prime. There's no superposition here with respect to the eigenkets of A. So if I start with an eigenket of an observable, and if I measure that same observable on that state, there's no uncertainty. You're sure you're sure to get a value, eigenvalue A prime, with probability 1. Right? So when we say that we are sure, it means that it has probability 1. Okay. So there's no uncertainty here. There's no uncertainty. All right. So clearly the dispersion vanishes when the state in question is an eigenstate of A. Now, roughly speaking, the dispersion of an observable characterizes the fuzziness. All right. So how much it's spread out. How much it is spread out. So if the state is not an eigenket of A, right? Suppose the state is not an eigenket of A, we'll be able to write the state as a sum over the eigenkets of A, right? We can write the state as sum of the eigenkets of A, all right? Now we don't know to which state it's going to change when we make a measurement, all right? Or as we consider this state is spread out over the eigenkets of A, all right? We see that the ket alpha here is spread out over the eigenkets of A. This means that there will be some fuzziness, all right? So there will be some uncertainty. Okay, so this is why we say that this characterizes the uncertainty of fuzziness. As an example, let's look at the SZ plus state of a spin half system. Okay, so the state is given to be ket plus, right? So the SZ plus state we earlier denoted as ket plus. All right, the dispersion of Sx can be computed to be, so we find the dispersion of Sx, the observable Sx, the x component of spin, right? We know that if the state is ket plus, the Sx eigenvalue is uncertain. It could either be plus h bar by 2 or minus h bar by 2. right? So we can find the dispersion of Sx like this. We can use the formula. We first take the square of the observable and then take the average minus, all right, minus, first I take the average and then the square. Okay, this is it. Now, so without going into a calculation, I leave it as an exercise to calculate this, all right, because we already know the form of the Sx operator in terms of get plus, bra plus, get minus, bra minus, etc. Right, so we already know the form for Sx. I ask you to substitute that here, find the square of it, substitute it here, and find this. All right, but we can understand in a different way also here. Okay, so this is the average value of Sx square. Right? We know that Sx has two values, plus h bar by 2 and minus h bar by 2. And in this case, we know that it has plus h bar by 2 or minus h bar by 2 with equal probabilities. The probability for h bar by 2 and the probability for minus h bar by 2 are equal. Right? These are equal. Right? So the possible values for Sx square would be h bar square by 4 and h bar square by 4, right? Squaring these eigenvalues, h bar square by 4 and h bar square by 4. And again, these are with equal probabilities, right? And we know these probabilities, the probabilities are 1 by 2. Okay, so the average value of Sx square can be written as the probability for measuring plus h bar square by 4 multiplied by h bar square by 4. Okay, this is the weighted average plus the probability for obtaining h bar square by 4. Right, so as the square of minus h bar by 2. Okay, and again h bar square divided by 4. So that's equal to h bar square divided by 4. Okay, this is the average value of Sx square. You can calculate it in the other way also. What about the average value for Sx? Clearly the average value is 0 because we have got h bar by 2 and minus h bar by 2. Right, so when we add a weight of half and add them, you get 0. Right, so from here you see that the dispersion in Sx, the dispersion of Sx in the state get plus is actually h bar square by 4. Right. Now, what about the dispersion of Sz square? Right. What about the dispersion of Sz square? Right. Clearly, that has to be equal to 0 because we already know that uh, there's no uncertainty. Right. In the state get plus, there's no uncertainty. For when you make a measurement Sz, there's no uncertainty. You are sure to get h bar divided by 2. All right, so let's find that delta Sz square, the average value of it. All right, we can write this as average value of Sz square minus average value of Sz squared. All right, so this is expectation value after squaring. This is squaring after finding the expectation value. All right, and we see that what's the average value for Sz square? We know that there is only one possibility here. It's h bar divided by 2. Okay, so this is Sz, this is one value for Sz. So for Sz square we'll have h bar square divided by 4. Right, so the average value here is actually h bar square divided by 4 minus what's the average value of Sz. Right, again there's only one possibility, h bar by 2. So average value of h bar by 2. All right, average value of Sz is simply h bar by 2 because there's only one possibility. All right, all the measurements on get plus of Sz will return a value h bar by 2. Alright, so the average value here is h bar divided by 2, but you have to square this average. Alright, so this is h bar square divided by 4 minus h bar square divided by 4, which is equal to 0. Alright, so we can say that in the get plus state or in the Sz plus state, Sz is sharp. There's no uncertainty. There's no uncertainty for Sz in this state. Okay, a vanishing dispersion for Sz, while Sx is fuzzy. There's an uncertainty. All right, we are not sure. We don't know what value we are going to get. It's all over the place. All right, there are only two possibilities, and it's uncertain. All right, it's fuzzy. It's dispersed. Okay, so we say that in the dispersion for so we say that Sx is fuzzy. Okay, so that's what it means. You might already be familiar with the position momentum uncertainty relation, also known as the Heisenberg uncertainty principle. So over there you might have learned that the product of uncertainties in x and p obey an inequality, obeys an inequality, right? Now we can actually generalize this, right? So this is the generalized uncertainty relation. You can consider it as a generalization of the xp uncertainty relation. So if A and B are observables, then for any state we must have the following inequality. This is the generalized uncertainty relation. Okay, so the mean square deviation in A, right, multiplied by the mean square deviation in B. Okay, this is greater than or equal to 1 by 4 modulus square of the expectation value of the commutator of A and B. Alright, so first you have to find the commutator of A and B, take the average, alright, take the expectation value, and then the modulus square, and then the modulus square. Alright, so clearly you see here that if the commutator is 0, then this is equal to 0. Right? If the commutator is 0, then this is equal to 0. Alright, the product of the mean square deviations will go to 0. Okay, this means that if you are talking about compatible observables, right, there's no uncertainty, or there's no uncertainty between them. There's no uncertainty between compatible observables. Right, we can determine the observable A and the observable B. We can measure observable A and observable B simultaneously without any uncertainty. Okay. Now to prove this relation, we must state three lemmas. We will be proving this using three lemmas. First one is the Schwarz inequality. Schwarz inequality says that bracket of alpha alpha multiplied by bracket of beta beta is greater than or equal to the modulus square of bracket alpha beta. Okay. Now this is understandable because bracket alpha alpha, right? So we are talking about a positive definite metric. So bracket alpha alpha is actually positive definite. It is positive definite. Similarly, bracket beta beta is also positive definite, unless they are null vectors. Right? We are not talking about null vectors here. We are not talking about null kets. Okay. So this is positive definite, and this is also positive definite. Right? But on the right hand side, we have got bra alpha ket beta. This could be 0. This could be even 0 because, for example, the special case where these are orthogonal kets, if ket alpha and ket beta are orthogonal, the right hand side would be 0, and on the left hand side, we'll have something greater than 1. Right? So here we at least see one instance where this relation is actually satisfied. Right? This is not enough. We'll prove this relation. It's a simple proof. Now this is analogous to this relation in real Euclidean space. Okay, modulus A square, modulus B square is greater than or equal to the modulus square of A vector dot B vector. Okay, so again we can see that here, when I take A vector dot B vector, this could even be 0. Right, but modulus A square is a sum of squares, ax square plus ay square plus az square. Right, and modulus B vector square is also a sum of squares. So these two are positive definite. Right, whereas on the right side it could be 0 in this case. Right, so you might already be familiar with this relation. Okay? So the analogous relation in the ket space, the analogous relation associated with the ket space is this. Okay, so let's prove this now. The proof for Schwarz inequality is quite simple. The first thing to remember is that if I have some ket gamma, right, if I take the inner product with the corresponding bra, right, any ket gamma, inner product with the corresponding bra, this has to be greater than or equal to 0. So we said that this is called the postulate of a positive definite metric. Okay, this is real, this is greater than or equal to 0. This has to be true for any ket. Okay. So this means that this has to be true for the ket gamma is equal to ket alpha plus lambda ket beta. All right. So if this is ket gamma, then we can write bra gamma as bra alpha plus lambda star bra beta. Okay. So the lambda here is a complex number. Now let's write this condition. Okay, bra gamma ket gamma, bracket gamma gamma is greater than or equal to 0 with gamma is equal to ket alpha plus lambda ket beta. Okay, so if I take the inner product of this ket with itself, right, or if we take the inner product of this ket with the corresponding bra, to be precise, all right, if we take the inner product of this ket with the corresponding bra, we can write it like this. We can write this condition like this: bra alpha plus lambda star bra beta, okay, multiplied by ket alpha plus lambda ket beta. This has to be greater than or equal to 0. It's the same thing. Okay. Let's just carry out the multiplication. Write it here. We've got more space here. Okay. So this we take bra alpha and combine it with every ket on the right side. Okay. So we have got first bracket alpha alpha plus lambda bracket alpha beta. Okay. Plus lambda star. I take this term lambda star bra beta ket alpha plus lambda lambda star bra beta ket beta. This has to be greater than or equal to 0. Now this relation should hold for any lambda. Lambda is just any complex number. It could be any complex number and still this relation should hold, which means that for any lambda this relation should hold, right? So we can try this relation for lambda is equal to minus beta alpha bracket beta alpha divided by bracket beta beta. Okay, so you just substitute lambda is equal to minus beta alpha divided by minus bracket beta alpha divided by bracket beta beta. Okay, we substitute this lambda in here. Okay, so the first term is simply, so with this lambda this term becomes, first term is bracket alpha alpha, right, plus lambda. Okay, so lambda has a minus here, this is minus bracket beta alpha divided by beta beta, and I have got this, I have substituted for lambda here, and this is bracket alpha beta. Okay, the next term is lambda star, right? So for lambda star, if I take the star of the numerator, this becomes bracket alpha beta. There's a minus sign here that remains, so star, the complex conjugate of bracket beta alpha, is actually bracket alpha beta, so this becomes bracket alpha beta divided by bracket beta beta. What is this? This is lambda star. Okay, and I have this term here, this is bracket beta alpha. Right, plus lambda lambda star. Okay, lambda multiplied by its own complex conjugate. Right, so the denominator here is real, positive. Okay, so when I take lambda lambda star, what I get is the modulus square of the numerator. Okay, so this is modulus square of bracket beta alpha. Okay, or we can write as bracket alpha beta. We can write as bracket alpha beta. Okay, modulus square of bracket alpha beta divided by beta beta square, modulus square, but since this is a real number, we can simply write it as a square, right? So remember that modulus square of bracket alpha beta is the same as modulus square of bracket beta alpha. Okay, so that's why I have written it like this. And then I have got a bracket beta beta here. This is the left hand side for this particular choice of lambda, and this expression says that this has to be equal to, right, or this condition says that this has to be greater than or equal to 0. This has to be greater than or equal to 0. Now if you look at the terms here, the term that appears here, this is bracket beta alpha multiplied by bracket alpha beta. Okay, this is nothing but the modulus square of this complex number. All right, similarly here I have got bracket alpha beta multiplied by bracket beta alpha, which is also the modulus square of bracket alpha beta. Okay, here I have got bracket beta beta square, and in the numerator I have a bracket beta beta. These are numbers, so I can cancel one of them, right? So these two terms, you see that these two terms are the same. Okay, and it's equal to twice modulus alpha beta square divided by beta beta. Okay, so I can write this as, this means, okay, I've got bracket alpha alpha minus twice modulus alpha beta square, okay, divided by bracket beta beta, and plus from here, okay, plus modulus alpha beta square divided by bracket beta beta. This has to be greater than or equal to 0. Okay, all right. Now this means that, let me write it here, this means that we have got bracket alpha alpha minus, this is minus 2, this is plus 1. Okay, the other terms are the same, so this is minus modulus square of bracket alpha beta, okay, divided by bracket beta beta. This has to be greater than or equal to 0, right? So we reached this expression starting with the basic postulate bracket gamma is greater than or equal to 0, right? It's the same thing. Now we could multiply throughout by bracket beta beta, which is a number. So you multiply throughout by bracket beta beta and you will get bracket alpha alpha multiplied by bracket beta beta. Okay, so this means, so this term when I multiply with bracket beta beta, it will cancel and I get minus modulus bra alpha ket beta square. This is greater than or equal to 0. Okay, this is exactly the relation that we wanted to prove. So we can, since we can write this as bracket alpha alpha multiplied by bracket beta beta is greater than or equal to modulus square of bracket alpha beta, okay, bracket alpha beta, modulus square of bracket alpha beta. This is the Schwarz inequality that we started, which the Schwarz inequality that we wanted to prove. Right? So we have proved the Schwarz inequality or lemma 1 that we need for the proof of the general uncertainty relation. Okay. So Schwarz inequality essentially follows from the positive definiteness of a metric. Okay. The second lemma that we need is that the expectation value of a Hermitian operator is purely real. Okay, so the proof is quite trivial. Because if you remember the discussion of Hermitian operators, we saw that in general, right? Let's say if you have something like bra alpha and some operator b ket alpha, or let's say ket beta. Okay. And if you need the complex conjugate of this number, we know that we have to write this as bra beta b dagger ket alpha. Okay, ket alpha. This is how we find the complex conjugate of this number, right? Or we can consider this as the definition for our Hermitian conjugate of an operator. Now, if an operator is Hermitian, then b dagger, if b is Hermitian, b dagger is equal to b. So we can write this as bra beta b ket alpha, right? This is if b dagger is equal to b for Hermitian operator. Okay. Now, what does this say about the expectation value of this operator? So for expectation value, I'll have the same state on the left and on the right. Okay. So let's find the expectation value of operator B, which is Hermitian. So using the same rule, instead of ket beta, I have a ket alpha here. So using the same rule, I see that bra alpha B ket alpha star is equal to bra alpha B ket alpha. Okay, so we have got a number which is the complex conjugate of itself, which means that this is a real number, or the expectation value of Hermitian operator is purely real. This can happen only if these things are purely real. Okay, there cannot be an imaginary part. If you have an imaginary part, then the complex conjugate will not be the same. Right? So this simple proof says that the expectation value of a Hermitian operator is purely real. So that's lemma 2 needed for our proof. We have got lemma 3. The expectation value of an anti-Hermitian operator defined by C is equal to minus C dagger is purely imaginary. Okay, the expectation value of an anti-Hermitian operator is purely imaginary. Okay, the proof here is also trivial. Again, let's start with this relation. We have got something like bra alpha C ket beta. This is a number. If I want to find the complex conjugate, this is equal to bra beta C dagger ket alpha. Okay. Now, if I want to find the expectation value of this operator, you have to use ket alpha here also. If I am using bra alpha here, I have to use ket alpha here. That was the definition for the expectation value. So this can be written as bra alpha C. This is the rule, and we have the expectation value of C is equal to bra alpha in the state alpha. In the state alpha. So this is bra alpha C ket alpha. Right? Now the same relation says that bra alpha C ket alpha star is equal to bra alpha C dagger ket alpha. Okay. Now for an anti-Hermitian operator, C is actually minus C dagger. Alright, or C dagger is minus C. So this means that this is equal to bra alpha minus C get alpha, or we get this result bra alpha C get alpha star is equal to minus bra alpha C get alpha. So when I get the complex conjugate, when I take the complex conjugate of this number, I simply get the minus of that number. I simply get the minus of that number, right? Now this is true only if these expectation values are purely imaginary. This means that the expectation values are purely imaginary. Means it does not have a real part, right? So if I have in general a complex number of the form a plus ib, if I take the star, I get a minus ib, right? It's not a minus of the first thing, right? So instead of a plus ib, I simply have ib, and if I take the star, I get the minus of the number that I started with. But this is purely imaginary. This is what we mean when we say that the number is purely imaginary. So this means that the expectation value of an anti-Hermitian operator is purely imaginary. Okay. So if the complex conjugate of a number is itself, then that number is real. Okay. And if the complex conjugate of a number is minus of the same number, then that number is purely imaginary. Okay. So that's what we have used here to say that the expectation value of an anti-Hermitian operator defined by C equal to minus C dagger is purely imaginary. All right. Now we have three lemmas. We can prove the generalized uncertainty relation using these three lemmas. Okay. The first lemma was the Schwarz inequality, which said that bracket alpha alpha multiplied by bracket beta beta has to be greater than or equal to the modulus square of bracket alpha beta. Okay, this was the first lemma, right? Now let's use the Schwarz inequality with these states. Ket alpha is equal to delta A acting on this empty ket. So this blank ket emphasizes the fact that our consideration here may be applied to any ket. So this could be any ket here, all right? This could be any ket. So if this is ket alpha, then the corresponding bra can be written as bra alpha is equal to, right? So this ket will become the corresponding bra, and delta A will become delta A dagger, but we are dealing with Hermitian operator, so this is simply the blank bra acted upon by the operator delta A. Okay, so we have got bra alpha and we have got ket alpha here. This means that we can find bra alpha ket alpha or bracket alpha alpha. We just use this, so this becomes, we have got an empty bra that represents any bra. Okay, and I've got a delta A here. This is bra alpha. Okay, so in ket alpha also I have a delta A and then acting on the empty ket. I can simply write this as delta A square between the states that we are considering. Okay, now this is simply the expectation value of delta A square. Right, this is the definition for the expectation value for delta A square. So I can write this as the expectation value for the operator delta A square. Okay, so bracket alpha alpha with this definition becomes the expectation value for delta A square. Right. Similarly, bracket beta beta here, we define bracket beta, or we write bracket beta as delta B acting on this empty ket or blank ket. This means that bracket beta beta can be written as the expectation value of delta B square. Okay. So we are just using the same states here, right? The ket that appears here is also the ket that appears here, right? Whatever that state is, right? Now we can also find the right hand side here. Okay, we need to find bracket alpha beta. So let's first find bracket alpha beta. Okay, that's equal to, I take the corresponding bra here. I've got the blank ket delta A, that's bra alpha. Okay, now ket beta is delta B acting on the same blanket. Okay, now on the right hand side I have got the modulus square of this, so I can find the modulus square of bracket alpha beta. Okay, modulus square is equal to, this is nothing but the expectation value of delta A delta B. Okay, so I take the expectation value of delta A delta B and then find the modulus square, all right. So I've found the left hand side. I've got bracket alpha alpha I've got bracket beta beta, and I also have modulus of bracket alpha beta, modulus square of bracket alpha beta. Right? Now I just put all this in the Schwarz inequality. So Schwarz inequality says that we must have average value of delta A square multiplied by average value of delta B square is greater than or equal to, right, the right hand side is this, modulus square of average value of delta A delta B, modulus square of average value of delta A delta B. Okay, this is what Schwarz inequality tells us. So we have used the first lemma. Okay, so from the first lemma we have delta A square expectation value multiplied by expectation value of delta B square is greater than or equal to the modulus square of the expectation value of delta A multiplied by delta B. Okay, so it's safe to put these brackets here to emphasize that we are talking about the square of delta A and not delta of A square. All right, that's not what we are talking about. Okay, so we'll put these brackets to avoid this confusion. I think in the previous slide I missed these brackets. Now the right hand side here, delta A delta B, the product of these operators, delta A delta B can be written in this form. If I have the product of two operators, okay, it could be, this is true for any operator. Okay, this can be written as half the commutator of delta A with delta B, okay, plus half the anti-commutator of delta A with delta B. All right. Now we already know the definitions for the commutator and anti-commutator. This would be delta A delta B minus delta B delta A. This would be delta A delta B plus delta B delta A. Right. So there's a minus delta B delta A from here, and there's a plus delta B delta A from here. They'll cancel. Right. And the first terms delta A delta B will add up with the delta A delta B from here, and there's this half. Okay, so that will cancel the 2 that appears when you add these first terms, all right, to give you back delta A delta B. Now this is true for any, this is actually true for any operators, all right. If you have a product of operators, you can decompose it into, you can decompose it in this form. You can write as half the commutator of operators plus half the anti-commutator of the two operators. Okay. Now let's look at the commutator delta A delta B. Right? If you look at this commutator delta A delta B, the first thing is that we can show that this is actually equal to the commutator of A with B. Now this is easy to show based on the definition of the commutator, okay, because delta A was equal to A minus average value of A and delta B was equal to B minus average value of B. You can try the definition and you will see that if I take delta A, the commutator of delta A with delta B, these cross terms will cancel off and you will simply get AB minus BA, or commutator of A with B. Right? I leave it as an exercise for you to prove and practice. Okay, so it can be easily shown based on the definition of the commutator that delta A delta B, commutator delta A delta B is actually commutator of A with B. All right, we could also use this property of commutators, which we have not discussed it, but we can write this delta A as A minus expectation value of A, comma, B minus expectation value of B. All right. Now this can be written as, you just distribute this. All right. This commutator, you just distribute this. You take the commutator of A with both these terms, and you take the commutator of expectation value of A with both these terms. All right. Remember that this is a number with an identity operator, and this is also a number with an identity operator. Right. So if I distribute this, I'll get commutator of A with B. That's one thing that I get from here. Okay. And then you have to take all other combinations. The second combination is commutator of A with expectation value of A with B. Commutator of expectation value of A with B. All right. This is a number multiplied by the identity operator, so it commutes with B. That's 0. Right. And then you get the term commutator of A with expectation value of B. That's also 0. Right. And then you have the term commutator of expectation value of A with this B, that's also 0. So all other terms will be 0. So you can easily show that the commutator of delta A with delta B is equal to the commutator of A with B. All right. So you should try this. Okay, try it based on the definition and just to get some practice in manipulating the commutators. Okay. Okay, back to this. Right. This commutator is equal to the commutator of A with B. All right. Now this is anti-Hermitian. This operator is anti-Hermitian. It's easy to show that this is anti-Hermitian, right? The Hermitian conjugate of commutator AB is the Hermitian conjugate of AB minus BA, and we know how to take the Hermitian conjugate for a product of operators. So this would become B dagger A dagger when I take the Hermitian conjugate, but these are Hermitian operators. So this B dagger is B and A dagger is A. So the Hermitian conjugate of this term will simply become BA, right? And the Hermitian conjugate of this term will simply become AB. Okay, what is BA minus AB? This is the commutator of B with A, right? Or this is minus the commutator of A with B, right? This can be written as minus of AB minus BA, or this is minus the commutator of A with B, all right? But if you look at this, right, if you look at the second term, this is actually Hermitian, right? This is anti-Hermitian and this is Hermitian. That's again easy to show because this anti-commutator by definition this is delta A delta B plus delta B delta A, and if you take the dagger you'll get exactly the same thing, all right? So we can now write the right hand side. Part of the right hand side, we have got the expectation value of delta A delta B can be written as half expectation value of commutator of A and B plus half expectation value of commutator of delta A, sorry, anti-commutator of delta A and delta B. Now from lemma 2 we know that, or lemma 3, we know that the expectation value of a Hermitian operator, or sorry, the expectation value of an anti-Hermitian operator is purely imaginary. Right now, since the commutator of A with B is an anti-Hermitian operator, this expectation value is purely imaginary. Right? Similarly, since whatever appears here is a Hermitian operator, the expectation value of the Hermitian operator is purely real. Right? We have got anti-Hermitian operator, the expectation value is purely imaginary. We have got a Hermitian operator here, so the expectation value is purely real. Alright, so we have just used lemma 2 and 3. We have just found the expectation value of delta A delta B is equal to half expectation value of commutator of A and B plus half expectation value of anti-commutator of delta A and delta B. Alright, this is what we have found. And we know that this is purely imaginary, and this is purely real. Okay, what we need to find, why we need this is to substitute in this expression that we found earlier. We had found earlier using Schwarz inequality that expectation value of delta A square multiplied by expectation value of delta B square is greater than or equal to modulus squared of the expectation value of delta A delta B. This we had already found from the Schwarz inequality. All right. Now what we have done is that we have calculated the expectation value of delta A delta B to be in this form. We said that the expectation value of delta A delta B can be written in this form. Okay, one is purely imaginary and the other one is purely real. Right. So this is of the form, let's say A plus IB. This is of the form A plus IB. Okay. Now if I look at the right hand side of this expression, this is what I need to evaluate. I need to find the modulus square of average value of delta A delta B. Let's find that. Right. The modulus square of the expectation value of delta A delta B. Right. This is equal to the modulus square of the right hand side. Right. But the modulus square of the right hand side is of the form A plus IB. Okay, so if I have a complex number z is equal to A plus IB, I can write modulus z square as A square plus B square, or I could write this also as modulus A square plus modulus IB square. This is also correct. Okay, this is a purely imaginary number. And what's modulus of IB square? If you want to check, this is equal to IB multiplied by minus IB, which is equal to B square, because I multiplied by minus I is 1. Okay, so I can write the modulus square of a complex number as modulus A square plus modulus square of IB. All right, or we can call this as purely real. This A is purely real and this IB is purely imaginary. So modulus Z square can be written as modulus square of the purely real part plus modulus square of the purely imaginary part. Right, that's what I have done here. We can write modulus square of expectation value of delta A delta B is equal to modulus square of this term, okay, the pure imaginary part corresponding to this here. Okay, if I take the modulus square, I have a 1 by 4, and then expectation value of commutation of A and B. All right. So this is 1 by 4 modulus square of the commutator. Sorry, modulus square of the expectation value of the commutator of A and B. That's a lot of words, but I think it's clear. Okay. And if I take the modulus square of this, I get 1 by 4 uh, modulus square of the expectation value of the anticommutator of delta A and delta B. Right. Now this is purely real. The second term is actually purely real. So if I take the modulus square, it's still real. It's real and positive. It is real and positive. All right. So suppose we have an expression y is greater than x plus 5. Okay. Now if y is greater than x plus 5, then y has to be certainly be greater than x. If y is greater than x plus 5, then y is certainly greater than x. All right. So it's the same kind of expression here. We have got, okay, let's first substitute this expression. All right. Let's first substitute this expression. All right. What is this? This is the modulus square of expectation value of delta A delta B. Let's substitute this into here. All right. What do we get? We get an expression like this. Let me write it down again. Delta A square averaged multiplied by delta B square averaged, okay, is greater than or equal to the modulus square here. The modulus square is actually written as 1 by 4 modulus expectation value of commutator of A and B, okay, square. Right. There's another term, but I can omit this term because of this reasoning. All right. If y is greater than x plus 5, then y is certainly greater than x. Now, since this is positive definite and I have got a greater than or equal to symbol here, all right. If this is greater than or equal to this entire term, then we can certainly say that it's greater than or equal to 1 by 4 modulus square of this thing. All right. So the proof. So we have actually proved what we wanted to prove. All right. This was the uncertainty relation that we wanted to prove. Okay. So the proof is now complete because the omission of the second term, the anticommutator term here, can only make the inequality relation stronger. Okay. Applications of the uncertainty relation to spin half systems is left as exercises. You can do these exercises just to practice with these things. Okay. Now we shall return to this topic when we discuss the fundamental XP commutation relation, right? The Heisenberg uncertainty relation. So here something that we see is that if the commutator of two observables is 0, or if the observables are compatible, then there's no uncertainty between them, right? So compatible observables can be the values, the measurement outcomes of compatible observables. All right. In other words, compatible observables can have simultaneous measurement outcomes without any uncertainty. All right. So this is something that we'll discuss again. So this is our generalized uncertainty relation. We can call this as a generalized uncertainty relation. We have the average value of delta A square multiplied by delta B squared averaged is greater than or equal to 1 by 4 modulus square of expectation value of commutator of A and B. All right. Okay. Now, again, as we said, if these observables are compatible, then there is no uncertainty. All right. The product of uncertainties, in a way, or the product of dispersions, product of mean square deviations becomes 0. Okay. Now, this can be understood based on what we discussed regarding compatible observables. Right? If two observables are compatible, we said that if A with B is equal to 0, the commutator of A with B is equal to 0, then they have a complete set of simultaneous eigenkets, which means that if you have an eigenket of A, it's also an eigenket of B. Right? And if you combine with this our measurement theory, if I start with the ket alpha and make a measurement of A, right, it ends up in an eigenket of observable A. All right. But if they commute, if this observable commutes, if A and B commutes, then the eigenket of A is also a state with a definite value for observable B. All right. So this state has a definite value for observable A. It also has a definite value for observable B. All right. So we can write this simply as ket A prime B prime. We have just used both eigenvalues to label it. All right. So this state is a special state in that it has a definite value for both A and B. All right. But what happens if A and B do not commute? If A and B do not commute, okay, if these are incompatible, then there's no such state. All right. We can find, if I make a measurement of A, I may get an eigenket A prime. All right. But this eigenket A prime would be spread, what do you say, it would be spread over all the eigenkets of B. This eigenket A prime will be written as sum over B prime C B prime ket B prime. Okay. Now if I make a measurement of B on this ket, if I make a measurement of B on this ket, I'll get any one of these eigenkets. I'll get any one of these eigenkets with probability modulus CB prime square, etc. Right. So we have to use probabilities there. So ultimately, all this is because of superpositions. All right. If an eigenket, if a ket A prime is a superposition of all ket B primes, okay, if I measure A on this system, it's fine. I'll get eigenvalue A prime. But if I measure B on this system, it will change to one of the eigenkets of observable B. All right. This is the reason for the fuzziness of incompatible observables. All right. So simply, there is no state which has a definite value for A and B if they are incompatible. Right? There is no such state. Right. So in more simple language, if you are talking about an electron, we have not discussed the position momentum uncertainty yet, but when we say that position and momentum cannot be determined simultaneously, what we actually mean is that there is no electron with a definite value of position and a definite value of momentum at the same time. Okay, there's no, we'll later see that the operators x and p do not commute. This means that they have no common eigenkets. In other words, there's no electron with a definite value of position and a definite value of momentum at the same time. Right? Simply, there's no such electron. That's why we are not able to measure it. It's not a problem with our measurement. Okay, such an electron does not exist. Okay, so if two observables do not commute, there's no state existing. There's no quantum mechanical state with a definite value for both A and B. There's no such quantum mechanical state. This causes the uncertainty. All right. It's not a problem with our measurement. It's not because our measurement disturbs the system or anything. Simply in quantum mechanics, such a state does not exist. Okay. So with that, I think we'll conclude the discussion of uncertainty relation. Thank you.